So welcome back. We are moving forward to our next module, that is module number 7. In this module, we are seeing a new topic that is related to quantitative techniques, and it is called as linear programming problem, short formed as LPP. In businesses, there are always some constraints which are involved. Like, for example, if you want to, you have a goal of maximizing something, that is, you try to maximize your profit or you try to minimize your cost. So when you have this kind of objectives, companies will always have some constraints which stops them from achieving what they want to. These constraints could be with regards to the resources they have, either the human, either the money or the machines, or the other things, other factors which will be forming as a constraint. So through LPP, we'll be seeing that how companies can actually maximize whatever objective they're trying to achieve with regards and forming, you can say, an objective function, and also forming finding out the constraints which are limiting the output of the system, and so on. So LPP is very useful for different managerial objectives which are there, and we'll just see that what are topics which we'll be seeing in this part. The first topic we'll be seeing is about formulation and solution to LPP. So when we speak about formulation, it means you have to have some proper formats which are there and which will help you to solve an LPP. So when you go for LPP, you always have something which is your maximization objective or your minimizing or your minimization objective. So these objectives are given by a symbol called as Z. So it can either be Z max or Z minimum. So the limitation, or you can say, obviously your things will be dependent on some variables. Some variables will be impacting your system, and similarly we can assume that some variables are there, or some decisions you're trying to make which have some variables which are involved. These variables are called as decision variables, and they are given by the symbol either X, Y, or whatever symbols you want to use, either X1, Y1, and so on. So your formulation of LPP will look something like this. You will have a Z max or a Z minimum. There will be an objective function. For example, I take 5x plus 4y as an objective. Maybe X can be the number of chairs, Y can be the number of tables which you are manufacturing as a company, and then you need to find out what are the things which are there. But there will be some limitations. These limitations are called as constraints. The constraints are always given by symbols like your less than equal to symbol or your greater than equal to symbol, and so on. These constraints are the limitations which are there for your manufacturing process or the system which you're trying to find out my objective function or maximize the objective function for. So if you observe here, in case of manufacturing, a constraint could be something which is limiting your machine capacity or it can be limited to the demand which is there in the market. According to that, you will have some equations. So this objective function will be subjected to these constraints, and the constraint could be something like this. The less than symbol is coming into picture. You can have a negative symbol also. Depending upon the equations what you have, what kind of equations have you created, the symbols and this signs will keep on varying, and your constraint will be looking like this. And to find, it's always a case that X and Y will always be greater than 0 and Y will also be greater than 0. That means it is a non-negative kind of it's a non-negative. It cannot be a negative number. It has to be a positive number because you're trying to check in a scenario which is related to your business. And yes, with this kind of formulation, you will be able to go ahead and solve the LPP. That is the next part. Will be solution. Here, to remind you that it is First is your objective function, which will look something like this. You will have your constraint equations, which will look something like this, and you have your non-negative constraint equations, which are there at the bottom. So every formulation or every numerical in LP would look something like this. The numerical will be given in words, and from words you have to convert it into a formulation, and it will be more dependent upon the way you analyze the question and the symbols. The major problem is the symbols which are there in the constraints which are there. It has to be done properly according to the requirement what the company has. A close attention forming this formulation of LPP. So this is the first part, that is formulation of linear programming problem. So when you go ahead for the solution is like we try to find out. I'll just rub this. So when we go ahead for solutions, the solutions are found out by means of a graph, or you can have a graphical representation of this line. So if you observe here, this is a linear equation which we have, and a linear equations which can be plotted on the graph. And linear equation will always give you a line, and from the line you can actually find out the initial or the feasible solution which is satisfying your requirement, the constraints, and from that you can find your answer. So your plotting is what we do on the graph. A plotting graph will look something like this. Maybe you will have something going like this. A line is going like this. Just an example. And you have two lines, and maybe your region will form somewhere over here. This is your feasible region. So if you observe this point A, this point B, and this point C, along with your origin, becomes your the trapezium, the square which has come up, or you can say a similar figure of not a square exactly, but a figure which has come here. If you observe, this portion is your feasible solution, and the solution for this kind of numericals is what we'll be seeing in depth, and we'll be finding out that how ABC will be able to satisfy the requirement, and from ABC, which is the thing which we could focus. So in this kind of an example, if you see that your chairs are X and your table is Y, so you need to find out how many are the number of chairs you want to manufacture, how many are the number of tables you want to manufacture in such a way that your profits are maximized, and also satisfying the condition of constraint we have, maybe a limitation related to our machines, or maybe a limitation related to the demand in the market. All these things will be have to be dealt in detail. So we'll be seeing all this, the plotting of the graph, the plotting of how the graphs are used to solve the LPP, how a feasible solution is there. There is something called as an infeasible solution also. If your region comes over here, it is more of an infeasible, and you have to make sure that infeasible solutions can also come up. So we'll be seeing all this type, what is an infeasible solution, what is a feasible solution, and how the final answer, that is solving the LPP, can be done in a better manner. So with that, we'll be focusing on the first part of this session, that is formulation and solution to LPP using graphical method. Now moving forward, there is something called as a simplex method. So in case of simplex methods, the limitation with this graphical method is that you cannot have more number of variables. So if you observe here, there are only two variables which we are using. But what if we have three variables? What if we have four variables? Maybe we have x1, x2, x3, and x4 also. Then what is the question? So in this kind of things, in this kind of scenario, we cannot use graphical method. Graphical method has its own limitation. So we go ahead to use something called as a simplex method. The word is simplex, but I warn you, the numericals are a bit difficult in simplex. The way we solve simplex method are quite complicated. It has a few number of steps which we need to follow, and from that step we need to get to the answers. So when we go for simplex method, there's something called a slack variable which we introduce, and this slack variable helps us to form the simplex method in the form of a simplex table, and from that simplex table, with the help of the slack variables, and we can form our solutions. So solutions will be similar to finding the value of x and y. That is the same thing, but we'll be using the method which is called as simplex method. So that is the second part of the chapter, which will be of the unit which we'll be seeing. And moving forward, the last part, that is a dual. So when we speak about dual, So it's like a dual. Everything it's like double or not double. It's like a mirror image, you can say, but not exactly the mirror image. So every linear programming problem has a duality factor in it, and duality is what exists in a linear programming problem. And this is a LPP problem. If you see this, observe here, this what I formed is a linear programming problem, and it will always have a dual. So dual makes it simpler for calculation, and basically you can check your answers with the help of. So when you create a dual, you will be actually seeing and solving it. Solution is similar to using a simplex method and getting the answers, or maybe you can use a graph, and on that basis you try to identify that how your linear the answers from your dual is matching with the primal function. You can say this is called as a primal function, which or the primal LPP program which is there, and your dual LPP program, are the answers coming out same or how is it? And all this can be done with the help of the dual. And yes, there is a simple thing that dual also helps you out to modify or cut down the calculations which are there. If you have n number of values which are there, like n number of variables, you can convert it into a dual problem, and then from the dual you can actually solve the LPP, and it will be better interpretations can be done from it, and we will be looking into that part also. So that part will be dealing with dual. So if you observe here, the dual can be formed from this term also. In this case, your limited becomes the objective, and the other, there's a transformation of the rows and columns, and the values of your objective becomes your constraints. That is the kind of a mirror image which I was speaking about. So that all we'll be seeing in the part of dual the duality of LPP, and how to interpret it, and that's what will be there. So in this chapter, thank you.